In this module, you will learn about thermodynamic state variables and equation of state. The cylinders shown are oxygen cylinders. Usually, when filled with the gas, all these cylinders contain equal quantities of oxygen. But how can an empty cylinder be filled with exactly the same quantity of oxygen? The ideal gas equation is PV is equal to mu RT, where P is pressure, V is volume, T is temperature, and mu is the number of moles of the gas. R is the gas constant. Hence, if the pressure, volume, and temperature of the oxygen in different cylinders are the same, they must contain the same quantity of gas. Since the volume of all these cylinders is the same at a given constant temperature, if oxygen is filled to a certain pressure, all these cylinders will contain equal quantities of oxygen. If oxygen gas in a cylinder is treated as a system, we can reproduce the system by knowing the values of some of the properties of the gas, such as mass, pressure, volume, and temperature. The set of values of properties of a thermodynamic system, which are used to reproduce the system, is known as thermodynamic state, and the properties are also called variables. The state of the oxygen gas in a cylinder is expressed by providing values of its pressure, volume, and temperature. If the values are P, V, and T, then the state is represented by P, V, T. Now, consider the general case of a gas in a container and let the state of the gas be represented by PVT. If the variables that describe the state, PVT, have uniform values throughout the system and they do not change with time, the system is said to be in equilibrium state. If A, B, and C are 3 points in the system, and PA, PB, and PC are the pressure of the gas at A, B, and C, and TA, TB, and TC are the temperatures of the gas at A, B, and C respectively, and if the state of the gas PVT is in equilibrium state, then PA is equal to PB is equal to PC is equal to P, and TA is equal to TB is equal to TC is equal to T. Not every state of a system is an equilibrium state. For example, if we suddenly pull the piston up, a vacuum is created above the gas, and the gas in the cylinder starts expanding against the vacuum. This is known as free expansion. During free expansion, the pressure and temperature of the system is not uniform throughout the system, and these values change with time. If P, Q, and R are 3 points in the system, and at these points the pressures are PP, PQ and PR, and the temperatures are TP, TQ and TR. Then PP is not equal to PQ, not equal to PR, and TP is not equal to TQ, not equal to TR. And these values at any point change with time. Hence, the state of the gas is not in equilibrium state. If the piston is completely removed, after some time, the gas is in mechanical and thermal equilibrium with its surroundings. If the pressure of the system is equal to the external pressure, then the system is said to be in mechanical equilibrium. And if the temperature of the system is equal to the temperature of the surroundings, then the system is said to be in thermal equilibrium with its surroundings. The variables that describe equilibrium state of a thermodynamic system are known as thermodynamic state variables. For example, if the pressure, volume and temperature of a given quantity of gas in a container is denoted by P1, V1 and T1, then its equilibrium state can be identified by P1, V1, T1, and P1, V1 and T1 are the state variables of this system. During any thermal process, if the equilibrium state of a system is changed, this is described by a change in the values of the state variables. If the gas in the container is compressed, and as a result if the pressure, the volume and temperature of the gas are changed from P1, V1, T1 to P2, V2 and T2 respectively, then the new equilibrium state is expressed by P2, V2, T2. As the name suggests, state variables of a system depend only on the state of the system, and they do not depend on the path through which the system is taken to attain this state. All the variables that describe an equilibrium state of a system may not be independent of each other. If pressure, volume and temperature of a given sample of gas in a container describe its equilibrium state, then the volume of the gas depends on its pressure and temperature. The relationship between state variables is called an equation of state. For a sample of mu moles of an ideal gas in a container, the ideal gas equation PV is equal to mu RT is the equation of state. From this relation, we can understand that of the three variables, P, V and T, only two are independent, and the third one depends on these independent variables. In the case of real gases, the size of the molecule is not negligible compared to the average separation between them. And the intermolecular attraction is also not negligible. By taking the above two facts into consideration, van der Waals has derived an equation of state for a real gas, which is P plus A by V square, V minus B is equal to mu RT, where A and B are constants. the constant A is related to the average force of attraction between the molecules, and the constant B is related to the total volume of the molecules. The state variables discussed so far are of two types: extensive state variables and intensive state variables. A state variable that depends on the size of the system is called an extensive variable. For example, the volume of a system depends on its size, and hence it is an extensive variable. Mass and internal energy are other examples of extensive variables. On the other hand, an intensive variable does not depend on the size of the system and has a uniform value in different subdivisions of the system. The pressure of the gas and temperature of the gas do not depend on the size of the system, and hence they are intensive variables. If a system of gas in a chamber, that is, in an equilibrium state, is divided into two equal parts, the variables that remain unchanged are intensive, and variables whose values are halved are extensive. We can see that there will be no change in the pressure, density, and temperature of the gas. Hence, pressure, density, and temperature are intensive variables. On the other hand, mass, volume, and internal energy are halved, and hence these are extensive variables. In any thermodynamic equation, quantities on both sides of the equality symbol must be either extensive or intensive. For example, the quantities on both sides of the following equation are extensive. Delta Q is equal to delta U plus P delta V, where delta Q is the heat exchanged, delta U is the change in internal energy, P is the pressure, and delta V is the change in volume of a gaseous system. Here, as delta Q depends on the mass of the system, it is extensive, and though P is intensive, the product P delta V is extensive. You have now reached the end of this module. In this module, you learned that the set of values of properties of a thermodynamic system that are used to reproduce the system is known as thermodynamic state, and the properties are also called variables. If the variables that describe the state have uniform values throughout the system and they do not change with time, then the system is said to be in equilibrium state. Not every state of a system is in equilibrium state. Free expansion of gas is not an equilibrium state. If the pressure of the system is equal to the external pressure, then the system is said to be in mechanical equilibrium. If the temperature of the system is equal to the temperature of the surroundings, then the system is said to be in thermal equilibrium with its surroundings. The variables that describe equilibrium state of a thermodynamic system are known as thermodynamic state variables. The state variables of a system depend only on the state of the system, and they do not depend on the path through which the system is taken to attain this state. The relationship between state variables is called equation of state. For an ideal gas, equation of state is expressed as PV is equal to mu RT. The equation of state for a real gas is expressed by van der Waals equation. P plus A by V square, V minus B is equal to mu RT. State variables are of two types: extensive state variables and intensive state variables. A state variable that depends on the size of the system is called an extensive variable. An intensive variable does not depend on the size of the system and has a uniform value in different subdivisions of the system. In any thermodynamic equation, quantities on both sides must be either extensive or intensive